my sincere thanks to the organizers, particularly Avinash, for giving me opportunity to share the podium. So, firstly, I should acknowledge my team members and my funding agencies. So, among the team members, there are students, and Aranyak and Saurabh are two very young colleagues of ours. Achinto is pretty known to most of you, and last but not the least, I am there. And these are the funding agencies who actually promoted our spray research. So actually we were in this area 12-15 years back when we started designing one atomizer on behalf of GTRE, the gas turbine research establishment. So then we started, and the thing is ongoing. So synthetic kerosene, so this is one fuel which we are really, the community is looking for long days. Maybe for last decades or 15 years, we are actually doing with these things. So there are a long list. I am not going into those things. Those are almost, we are discussing all the things here. Now, the main aim is to decarbonizing the aviation sector. So why is it really required for decarbonization? That is well known, because your synthetic kerosene, it is taking atmospheric CO2 and it is again pushing it back there in the atmosphere. So basically the carbon footprint is technically or theoretically zero. So we are calling it sustainable aviation fuel, so which can reduce our emission by 80%. And up till now, we can say that safely we can go up to 50% blending for the aviation fuel with synthetic fuels. But there is a good news that in 2021, United Airlines had one experiment, and they demonstrated this thing, that 100% ASF they used in the engine. But okay, but let us see how long we can go for that for commercial purpose. Actually, the problem is our cost now. So what Dr. Sharma was pointed out in the very first plenary lecture, that the cost at present, it is somewhere here. It is 2.5 euro per liter. Whereas our regular kerosene we can find at, say, of the order of 1 euro per liter. But there is a good situation in future, that is in 2050 the cost will come down. So we can go ahead in that direction. Now we can use diesel kerosene blend in IC engine also. The main reasons are basically these three, basically these two, because we are reducing the emission, but we are compromising some amount of BSFC. So the finding is up to say 7 to 14% if you blend the kerosene, the significant loss of BSFC is not there. Now there is a question, can I replace it with e-kerosene? So if you want to replace it with e-kerosene, then we need to look at the property values of the e-kerosene, whether those are similar to our regular kerosene or jet fuel. So here lies the answer. So this part are our conventional thing, and these are the points for different grades of our synthetic kerosene. So the properties are pretty similar. And if we look at the calorific value also, then also we can see that calorific value of the synthetic fuel is similar to our regular kerosene or the jet fuel. Now, if I think about the spray characteristics, mainly these three are the properties: your density, your viscosity, and your surface tension, which are actually governing the major aspect of your spray. But there is another member, we will look into it separately. So as these three are pretty similar, so we can think about the spray characteristics of e-kerosene in light of our kerosene research earlier, what we have done. So the question is, are their sprays similar? So if we think that these three things are similar, so we can start with at least a preliminary idea that okay, our spray characteristics will be pretty similar. Maybe not exactly similar, but it is almost similar kind of a thing. So there was one experiment that is with a nozzle. So if you look at the spray characteristics of three things, that is, one is your SAF, one is your pure jet fuel, and one is your blend. So it is very hard to differentiate between the characteristics because those are pretty similar. And if you look at the mean and short-term mean values, those are also similar. So these are at three different pressures, and these two are at two different locations also. So we can say that covering the whole spray angle, we are getting a pretty similar feature. So these are the extract from the earlier thing, so there is no need to explain it more. So now let us come to our atomizer. What we started with GTRE. So it was a hybrid atomizer. Hybrid means it is a mixture of pressure swirl and air blast kind of a thing. So the design is a bit complicated. There are actually three lines. There is one central air line, one annular fuel line, and one annular air line. And if you look at the situation, you can change the direction of flow. And so what you can do, you can, for the central line, you can go for a straight flow, you can go for a swirl. For outer, you can go for a swirl, and for fuel also, you can go for a swirl. So there are many combinations we can have. So what we saw there, the breakup types are not very simple. Like this is one, this is another. So depending on the flow regime, depending on the flow directions, we can have different types of breakups which we are experiencing with our standard kerosene. And obviously, as our property values are pretty similar, we can have a similar kind of a breakup pattern for the synthetic fuel also. So we have experienced these 6 kind of a situation for different kind of flow rates and different kind of flow orientation. So if I show you this is for 1 LPM kerosene and with co-flow of outer air and inner co-swirl. Inner co-swirl means the inner air and fuel is swirling in the same direction, and outer air is also coming in the swirling in the same direction as fuel. So you are getting this kind of a thing. So in a particular orientation also, as you are changing your velocity, you are getting different kind of breakup regimes. So similar thing you will get for if you go for inner counter swirl. So fuel is moving in one direction, your inner air is moving in the another direction, and outer is moving in the another direction. So what we did, so this is our, we tried to plot this breakup regime for different conditions. So we thought that firstly this thing is required for this kind of a breakup situation, for what case we are getting what kind of a breakup, and then we can say we can go for the measurement of different breakup parameters. So this one is for kerosene. We and if you look at the thing, that you can see that this is actually not for pure kerosene. We go for some kerosene and methanol blend also. So we did the same thing for diesel, and also with diesel alcohol blend. I am not going into the detailed data for this, because you can find those in the publications. Now what we got recently, that is one paper which came in Fuel in this year. So one experimental study, and we tried to model it. So with their experiment and our modeling, we tried to map this. This is at different time instance, and if we go for diesel kerosene spray, diesel and kerosene blending, where kerosene is 50%, diesel is 50%, so then we can find this kind of a situation. So if I quantify the thing, here one mistake is there, this will be in meter, not in millimeter. So you can see that our computation is under predicted in both the cases, in case of kerosene, in case of the blend. Now why is this under prediction? So basically we actually taken this DPM model, that is discrete phase modeling. What it does, it takes a monodisperse spray of the shorter mean diameter. So basically what is happening, when you are taking a shorter mean diameter monodisperse spray, you are actually neglecting the smaller diameters and the higher diameters in your spray regime. So as the smaller diameters are thrown to a longer distance, you are not able to capture that in your modeling. So what is happening, our modeling is actually under predicting, but we can rectify this, because as we know what is the reason. Now if I go from monodispersity to polydispersity, and if I take a particular kind of a distribution function, I can take the effect of the smaller droplets, and I can take the throw of that, and I can fine tune my distribution for this kind of a experimental thing. But the life is not so simple, because we will have to take care of the volatility. And here lies a problem. If you look at this thing, this blue are for A2, A2 means your conventional fuel, and C5 is your SAF. So you can see that the C5, the penetration is less. When you are measuring the droplet penetration, the penetration is it is showing in experiment that your penetration is less. What is the problem? Problem is, if you look at the volatility curve, you will see that volatility of this is higher. So what is happening when you are seeing the spray in a liquid domain, in a droplet form, actually before that some amount of fuel is vaporized. So if I try to model my thing properly, then I need to take care of the volatility along with my distribution function of polydispersity. So that is not really a very easy task for the modeling persons. But we are on it. I won't say we are on it, I should say our young persons will be on it. So they will take care of that and they can do the thing, that is my belief. So for summarizing, I need not to tell much. One thing is e-kerosene is sustainable and scalable, there is no doubt of it. But experimental data generation is required because we will need to go for a proper CFD model. So, and if you need to go for a CFD model, you need to go for good amount of experimental data and you can, so that you can match. So, model generation of breakup is required. Thank you.
And just in time, congratulations. Maybe there are questions?
Yes, Chetan.
So you also tried modeling for reactive condition?
No, not yet. So the modeling, what I shown you, that
is non-reactive. So
if you talk about this part, it is here you are not really taking care of the reaction because we are not going into combustion.
yeah.
But here we have not taken care of the volatility, the evaporation of the fuel. But when you are doing the experiment, evaporation is there.
Yeah.
Okay, so that's why
I'm just asking
here we have not yet taken care of the volatility.
Okay. So because when there is a incident of combustion, it will be not easier.
It is not easier. It is the very complex kind of a modeling.
Okay.
But okay, we'll have to do it.
You also tried for, you also have experimental facility, right?
Yeah, we have some.
So you did some combustion,
Combustion in which area?
in this.
No, we have not tried combustion with this particular atomizer. But maybe in future we will try to do that. Okay.
It will be interesting. Yes. Okay. Thank you.
I have a question. Someone else has a question? You have a question? Please. Take the microphone.
I have two quick questions. First one is we have distribution like RR distribution.
Pardon?
Rosen Ramler distribution and Chayescliffe distribution for initiating the spray in blob irrigation. But we also have experimental data, but this 30 mm or 40 mm downstream. So can we actually use the distribution at 30 mm downstream for initializing the spray? Assembly distribution or because near the nose
Okay,
the
I
experimental
can
data.
talk with you later on because I will have to understand the thing first.
Okay.
But one thing you can do, you can assume a distribution at the mouth of the nozzle, and then you'll have to fine tune. You have to change the distribution and you have to see what you are getting at
Yes,
down the
that's
stream.
downstream. Another thing is apart from evaporation and this thing, there is coalescence. So are we also considering coalescence modeling the principal reason?
No.
Because
I have not considered yet, but that is there.
yeah.
That is there because if you have a very small droplets, there is a typical chance of coalescence.
Actually, we did some experiments.
Actually, that part of modeling is really very complicated. I think Professor Panikrai can also share some of his experience of fluid mechanics. Actually, secondary breakup is really very challenging. I have not done it at least.
Okay, thank you. Could you show the comparison modeling and experiment? Your slide. It's the next one, I think. Or the previous one is was yes, this one. I wanted to know the details about the simulation. Is that a Lagrangian or a Eulerian?
It is Lagrangian.
Lagrangian.
Lagrangian means say
Yes. And the second question is the geometry of the injector?
this is the model, the discrete phase model. So that means you are actually putting the droplets there and you are tracking it Lagrangian inside the flow.
Yeah. But the geometry of the injector is taken into account or not?
It is actually inside the geometry we have not taken
Okay.
because it's a very it's a simple nozzle.
Okay.
So orifice kind of a nozzle, not even a pressure swan. So what we did, we have taken the pressure difference and we assumed the velocity at this location.
Okay, I
And with
understand.
that velocity we actually solved.
Without evaporation.
Without evaporation.
Okay.
But in this paper we have the data with evaporation.
Sure.
So now we'll have to try for that.
And steady air. The air around the droplet is steady.
Yeah, it is steady. It is steady.
Thank you very much. Another question?
So how you get the information of this velocity?
That is, you have the information of the pressure difference.
Okay.
So what we assume that with the pressure difference we have calculated the velocity at the nozzle mouth.
By a Bernoulli.
Or what you can do if you can give the nozzle geometry, then also you can have a better velocity distribution.
Okay. Thank you very much.
Thank you.
Long live India and France friendship.